Hello, welcome to this presentation about numeric web search. Web search is up to now language-based, and it would be possible to combine this with a similarity search. This is numeric web search. The search object would be such patterns. They consist of a pattern name, which begins with a conventional domain name, and of a feature vector. The feature vector can very precisely describe all measurable objects, and more. Therefore, numeric web search has great potential. It would be advantageous to allow every owner of an internet domain name dn the right to define all patterns whose names begin with dn. So we could mobilize a great working potential. After this short summary, some details. Now, try to explain the position of this point using conventional language. You may use a formulation like this. The point is near to the left margin, but not very near, and it's close to the bottom, but not very close. And of course, this is not a precise description, and because the description is not precise, you cannot make a precise search. To make this, you need a more direct way. You need to make a measurement to measure the distance from the left margin, and from the bottom, put the two resulting numbers into a vector structure, and search on the web for a similar vector, simply by calculating the distances to these comparable vectors on the web. And in the search result, those vectors with minimal distance would be listened first. This means that those objects with similar coordinates are listened first. So you can make similarity search for all measurable objects and for more, because all measurable objects can be very efficiently represented by sequences of numbers or feature vectors. And unique names can be used for quick identification. The most efficient way to identify some object, some feature vector, is to give the object a name. Subsequently, feature vector with name will be called pattern. The pattern structure is as simple as possible to introduce numeric web search. Here's the pattern name, which identifies the meaning of the new numbers which are contained in the feature vector, and some auxiliary data. Here you see the XML representation of the pattern. Here's the pattern name, and here the feature vector, and some further auxiliary data, for example, URL of an object which is associated with this pattern. For example, if the feature vectors represent some measurements on a face, this may be the URL of the photo of this face. And to mobilize a great working potential, it would be advantageous to allow every owner of an internet domain name to define all patterns whose names begin with his internet domain name. All these definitions could be placed on a unique location on the web. Here's the domain, and in the subdirectory path there could be placed all definitions of patterns whose names begin with the domain name dn. So we have, for every pattern name we advance we know where the definition is. And we could also locate templates which can make the feature vectors human readable. For example, if the feature vectors in this case represent three numbers which represent the length, height and width of some object, you could put the three numbers into a template and both together give a human readable sentence. Here is a further, in the directory with definitions, there is a further machine readable file which is necessary for the search engine, that it can identify, for example, the metric which should be used for comparison. The number of the metric is here listened. And here are some advantages of the pattern structure. And the most important advantage is that patterns are numerically searchable, using a simple concise metric, because the feature vectors are also comparable. And here an example from feature vector, GPS coordinates. Alone this definition would allow to combine local search with conventional language search. For example, using this definition, you can search for shops or specialists for doctors and so on near a special location. Here another example, price in dollars. If you are looking for some object for sale, you can look for this pattern. If you may want to buy the most cheapest object, simply make a search for a pattern with price 0. And to the nearest objects to 0 are those objects which are the cheapest objects. And another example, a pattern which some measurements of length, width and height of some object, or here some industrial specification, for example here electromotors. If a manufacturer of electromotors wants to make his products searchable all over the web, he may define a pattern structure. The first number may be of the feature vector, the first number may be the power in watt, the second number the revolutions per minute, and so on. And so he can make his products all over the web searchable. And of course it is also possible for clothes. If you have some special measurements on your body, you can search for clothes which have similar measurements like your body. So can you make best fitting clothes? You can search for best fitting clothes. The origin of the idea is in medicine. In orthodontics you make very much measurements on the, for example in cephalometry, and also for scanned teeth. And all these measurements can be packed into feature vectors, and we could make similarity search and blend databases. And then we noted that it's possible to generalize this, to make also feature extraction from other medical findings, for example skin photos here. Is this dangerous or not? You can store all these findings, all these feature vectors can you store in a database and observe this, and after some years you know which findings are dangerous or not. If now a future patient comes, you can make the same feature extraction on his findings and look in the database whether his findings are similar to the dangerous ones or not so dangerous. And here another example, it's a programmed example. You can make also similarity search for heard sounds. In this case, the feature vector is calculated from the wavelet decomposition of this heard sound, and the resulting the feature vector has 4000 numbers in this case, and also in this long feature vectors you can make similarity search, and here are the most similar heard sounds to a given heard sound are listened first. Here a typical example, you have an MRI picture, here is an osteoporotic fracture. You can make measurements on this picture, put all these measurements on a feature vector and store all these findings in a global database. And you can, if you store a great number of cases and you have then some future cases, you can make the same measurements and look in the global database for those patients which have similar measurement results and look for the treatment which has been most successful, globally most successful for such findings. And this is a very precise description, much more precise than language can do. So we can get more objectivity in medicine, and I think this would be a great advantage of this. If you are interested, you can get more information if you look at this web page. Thank you for your attention.